Until now, we have formally introduced two different types of energy, which are the kinetic energy represented by the symbol K and potential energy represented by the symbol U. Now let's give these two energy a formal definition, and at the same time we look at what are the parameters that affect these two energies. So kinetic energy, we call it as the energy associated with the motion of an object. So if an object moves, it will have some kind of speed, therefore it will have kinetic energy. So if an object has a faster motion, or we can call it greater speed, then it will cause the object to have greater kinetic energy. So this is expressed in the form of the equation. Kinetic energy equals to half mv squared, where m is the mass, v here represents the speed of the object. So faster motion, greater speed, greater v means greater k, therefore greater kinetic energy. Okay, next we look at potential energy. Potential energy is the energy associated with the position of an object. Well, remember that we create this idea of potential energy when we talk about the work done by conservative force, right? So work done by conservative force, it's independent of the path we take to go from the initial position to the final position. Therefore, what we care about is only the position, the initial and the final position only. That's why potential energy is the energy associated with the position of the object. It doesn't depend on the path. Okay? So we have two different types of potential energy in chapter 5. One is the gravitational potential energy represented by U subscript G. So for gravitational potential energy, a greater height will result in greater gravitational potential energy. So this is expressed in the equation U subscript G equals to mgh. So gravitational potential energy equals to mass of the object, gravitation acceleration due to gravity experienced by the object, and the height of the object. So these are the parameters that control our gravitational potential energy. Another kind of potential energy that we have is the elastic potential energy. So elastic potential energy is due to the conservative force, which is the restoring force of a spring. So for elastic potential energy, if you have a greater stretch or you have a greater compression of your spring, then you result in greater amount of elastic potential energy being stored in the spring. So this is expressed in the form of equation U elastic equals to half kx squared. So elastic potential energy is equals to half times the spring constant times the amount of stretch or the amount of compression squared. So you can see the amount of compression is directly affecting the elastic potential energy. Now we have stated the definition for kinetic and potential energy. We look at another kind of energy, which is the sum of the kinetic and potential energy. So if we sum up kinetic and potential energy, we call that sum by another name, which is the mechanical energy. So mechanical energy, we can represent it by the symbol E. So E here doesn't represent energy. E here represents mechanical energy. And in chapter 5, E represents mechanical energy. So what is mechanical energy? Well, you can call it just as the sum of the kinetic energy and potential energy. And if you look at it mathematically, it's kinetic energy plus the gravitational potential energy and elastic potential energy. So this is for chapter 5, because the two potential energy that we encounter in chapter 5 are the gravitational and elastic potential energy. Okay, we can also re-express mechanical energy with another definition, which is the energy associated with the motion, the kinetic side, and the position, the potential side of an object. So, well, it's just another way of saying that it's a sum of kinetic and potential energy. And lastly, in certain books, you also encounter the definition saying that mechanical energy is the macroscopic energy associated with a system. Well, this one is slightly more confusing how to explain it. I can think of it like this. For an object, right, in our study of mechanics, which is how things move and why things move the way it moves, right? In the topic of mechanics, when we look at an object, we only care about how it moves. So we care about where is the object now and how does the object move with time. So if these are the things that we care about, then of course the energy that we care about will be the energy associated with where is it right now and the energy associated with how is it moving right now. So it's the energy associated with motion and position, and therefore it's mechanical energy. So that's how you can think about it. Okay, so before we end this video, I would like to talk something about potential energy. So potential energy, right? If you have done SPM questions before, have you ever wondered why occasionally I put my tabletop as h equals 0? Occasionally I put my floor as h equals 0. Like at different situation, sometimes I can put the ground as where my potential energy is 0. Occasionally I can put my tabletop as where my gravitational potential energy is 0. Well, that's because potential energy, right? The reference position can be set by ourselves. What is reference position? Reference position is the position where we set our potential energy to be 0. So we can for, let's say, for gravitational potential energy, right? We can arbitrarily set a position and say this is the position where I want the U to be 0. Then if you are above that position, then you have a positive gravitational potential energy. And if you are below the reference point, then you will have a negative gravitational potential energy. And that point, right, you can set it as anywhere. So in your SPM, you have probably seen situation where you set your ground as where your gravitational potential energy is 0, h is 0, then u is 0 for your ground. Occasionally, you set it on the table. So if an object is on the table, it has 0 gravitational potential energy because you set the table as the reference position. And occasionally in future chapters, you said occasionally we can even put the top of the hill as the reference position. So as long as you haven't reached the top of the hill, your gravitational potential energy is negative. And in chapter 7 later, we'll talk about gravitational force. You see that we can even set a point far, infinitely far away as the point where we set as reference position. So we can say at the infinite position, we set our gravitational potential energy to be 0. And at that point, things can get a bit funny because all the gravitational potential energy that we encounter will be negative because we are always below the infinite point. But let's don't talk about that. That's chapter 7. Let's leave it to chapter 7. So for gravitational potential energy, where we set as our reference position depends on where it's convenient. And occasionally it depends on the question as well. But for elastic potential energy, we don't have that kind of flexibility anymore. For elastic potential energy, right, the reference position is always the position at which the spring is neither stretched or compressed. So you can never set a position where the spring is stretched or compressed as the reference position. You cannot do so. You can only set the position in which the spring is neither stretched or compressed as the reference position. And that is where our x is equals to 0. Our spring doesn't stretch, doesn't compress. Therefore, x equals to 0. Your U elastic will be equals to 0. So that's the idea of reference position, and it's good to know that you can arbitrarily set where you want to be your reference position for gravitational potential energy.